Hi everyone, welcome to Mostly Math. Today we'll be deriving the power rule using infinitesimals. We'll be considering the definition of the derivative to be df by dx to be 1 over epsilon times f of x plus epsilon minus f of x, where epsilon is an infinitesimal. In physics we use infinitesimals instead of limits. Basically, epsilon is the limit as h goes to 0 of h that you've seen in the typical definition of the derivative. We're just going to use the infinitesimals because we don't have to carry around the limit sign since we're lazy physicists. We just don't want to do that. And we can simply let epsilon go to 0 at the end of our calculations anyways. All right, let's start off by evaluating this derivative before we tackle the whole thing. d by dx of x squared, just 1 over epsilon x plus epsilon squared minus x squared, which is 1 over epsilon. Expanding this using the FOIL method, or your other favorite method. X squared plus 2x epsilon plus epsilon squared minus x squared. Okay, got some x squareds canceling. This becomes 2x plus epsilon, which goes to, as epsilon goes to 0, 2x. Yep, that should certainly look familiar to you and show you that we can still take derivatives using the infinitesimal method. No problem. All right, before we do the big case, we have to go ahead and write down the binomial expansion, since we'll be using this. Instead of x plus epsilon squared, we'll have x plus epsilon to the nth power. So if we use this expansion, it tells us that x plus y to the nth power is just the sum from k equals 0 to n of n choose k, the binomial coefficients, x to the n minus k, y to the k, where the coefficients are defined to be n factorial over k factorial, n minus k factorial. Excellent. Now let's begin. That's all we need, really. So the derivative of x to the n is now 1 over epsilon x plus epsilon to the nth power minus x to the n, 1 over epsilon. Okay, let's do the sum. So we have the sum from k equals 0 to n of n choose k, x to the n minus k, epsilon to the k, minus x to the n. Now we have a sum here, and we have a power of n here, which we hope would cancel out. So to cancel it out, we're going to start by evaluating the k equals 0 term and keeping the rest of the sum intact and seeing what happens. All right, this is just 1 over epsilon. Sum, well, first of all, yep. So let's just evaluate the k equals 0 term first. Okay, so we need n choose 0. Not very hard. N choose 0 is just n factorial over 0 factorial, which is 1, times n minus 1 factorial, which is n minus, oh, sorry. This is the wrong one. This is actually n, sorry about that. I was getting ahead of myself, which is 1, and just n factorial over n factorial, which is 1. All right, so this term is just 1 times x to the n, epsilon to the 0. We have the second term of the sum here, starting k at 1, and choose k, x to the n minus k, epsilon to the k, minus x to the n. So we see that these two do cancel out. Fantastic. We'll take the epsilon and decrease this power by 1. Sum from k equals 1 to n of n choose k, x to the n minus k, epsilon to the k minus 1. Okay, fantastic. Now we're going to peel off the first term, the k equals 1 term. Well, the k equals 1 term is just going to require us to evaluate n choose 1. Okay, let's do better this time. So we got n choose 1 to be n factorial over 1 factorial, which is 1 again, over n minus 1 factorial, which is n minus 1 factorial over n minus 1 factorial, which is n. Excellent. This is just going to be n times x to the n minus 1 power. Epsilon power is 0, so it's not here. Plus the sum k starting at 2 now to n of n choose k epsilon n minus k. Sorry, x to the n minus k epsilon k. Okay, and now if we're careful, this can be the last step. So k starts at 2. So the first power of epsilon is going to be 1. So we got epsilon here. And the term after that is going to be, epsilon squared, epsilon cubed, and so forth. This is just proportional to epsilon and epsilon squared and all higher powers. So as epsilon goes to 0, we really don't care about this term. This becomes 0, and our final answer is nx n minus 1, which I hope you do recall from an elementary calculus class. Fantastic. That's pretty much what we set to accomplish, but let's think about for which values of n that it works for. Since we're used to just putting in any value of n, but let's see if the proof that we did actually can hold for any n. Spoiler alert, no, but I'll tell you which ones it does work for. Okay. Question: for which n does, sorry, can't spell does today, does the binomial expansion hold? Well, as stated, actually only works for positive integers. So right now we have n positive integer, good. So n is a 1, 2, 3, etc. I guess you can include 0 in this. Yeah. Trivial case, we don't really care about it very much. This one's fine. These are the numbers that the binomial expansion holds. With a slight modification, we can actually have it hold for some p an element of the rationals as well. So we can get the negative integers now, and we can get half and negative 5/7 and things like that by doing the Newton expansion. Basically, all we have to do is modify the binomial expansion to let the sum go to infinity now, and there's a slightly different definition of the coefficients as well, but we don't need to worry about that now. Basically, we'll be doing x plus y to the nth power, or the p power, rather, in this case, to be sum k equals 0 to infinity now. P choose k, x to the p minus k, y to the k. That's all we have to do to have this proof hold for the rational numbers. Great, that's pretty cool. How about for the general real numbers? So everything we've done before, but also including irrational numbers like the square root of 2 and transcendental numbers like pi. Can we modify this proof somehow to include these? No. No, we can't. We cannot, because we would actually be defining x to the n for n, say the square root of 2, an irrational number, to be e to the square root of 2 log x. And there's just no way to modify the expansion that we've been doing to cover this case. But that's okay. There is a pretty quick and easy proof to get that one as well. It's the same in both the math and the physics courses. It's not that interesting, but it's important to know. So here's how we can get all the real numbers. So take the derivative of x to some real number now. So x can now be square root of 2 and e, which is just defined to be the derivative of e to the r log x, which, that's pretty simple. We just take e to the r log x times the inside derivative, so that becomes x to the r. Derivative of inside is, well, log of x has a 1 over x derivative, so this becomes r over x, which is just r x to the r minus 1, which we showed earlier. So now you're probably asking, well, why didn't you just do this proof? Well, it's important to do the proofs with the expansions, because when you first encounter this in calculus, you'll see it for n equals 1, 2, etc. and you want to basically perform induction upon your intuition to see where it can take you. And it takes you here, and to get the next step, well, it's a different structure, but you can get it as well. So the power rule holds for all real numbers. If you enjoyed this, want to see more, please subscribe. Have a great day.